So, hello everyone again. This is lecture 10 part 3 of semiconductor electronics, materials, devices and simple circuits. In this lecture we will move on to the problems regarding transistor as a switch, transistor as an amplifier I guess, and then we can move on to the final discussion regarding transistor, which is how to use it as a oscillator. So, let me start the discussion directly. I am Sameer Lavankar. Let us begin our discussion. So, currently we are in the transistor circuits. After this is being completed, we will move on to the final two discussions regarding digital electronics and logic gates and finally integrated circuits. So, let us start today's discussion regarding the first example. So, please look over here carefully. So, as you can see in figure A, the VBB supply can be varied from 0 to 5 volts. So, this value of VBB can be in the range of 0 to 5 volts. Okay. The silicon transistor has beta DC as 250. What is the meaning of beta DC? Beta DC is basically the amplification factor, correct, or the current gain, and RB is given to you as 100 kilo ohms. So, this value is given to you as 100 kilo ohms, RC is given to you as 1 kilo ohms, and VCC is given to you as 5 volts. Okay. Assume that when the transistor is saturated, VCE is 0, VBE is 0.8 volts. So, they are just telling you the assumptions being obtained or being understood when the transistor is saturated. So, first question is that we need to understand we need to calculate the minimum base current for which the transistor will reach saturation. Okay. So, we just first of all we need to calculate the value of IB. Okay. To calculate the value, let us first understand the complete concept, what they are trying to make us understand. First of all, we need to calculate the value of IB. To calculate the value of IB, in some sense or another, we should need the value of IC. How is there a relation between IB and IC? We have the relation which is beta DC. So, one relation is being obtained using beta DC. Next concept is, do we know the Kirchhoff's rule to apply here? We know the Kirchhoff's rule to be applied here, correct. Next thing, they also gave us that what is the value of VCE. If VCE value is already given to us, that means we need to use the Kirchhoff rule at the output region. Okay. So, just try to use it and the question is done. So, first of all, at saturation it is already given to you as that VCE is 0 volts and VBE is 0.8 volts, right. So, first of all, let me use the Kirchhoff's rule at the second loop. Therefore, what is VCE? VCE is nothing but equal to VCC minus ICRC. As this value of VCC is 0, what we will do? We will do basically IC is nothing but VCC by RC. Is the value of VCC given to you? The value of VCC is given to you. Is the value of RC given to you? The value of RC is given to you. Just input it, you will get the value of IC as 5 milliamperes. First thing is done. Next thing is if the value of IC is known to us, beta DC is known to us, can we calculate the value of IB? Because beta DC will be constant, it is DC, so it is direct current, it will not change. Okay. Therefore, what is IB? IB is nothing but equal to IC by beta, or we can directly write what is beta. Beta is basically IC by IB. Quite evident, as IC is a greater value because it is being amplified in the further sense, or IC is always greater than IB, correct. Therefore, we can directly write that it does not matter that it is amplified or not, IC will be greater only. So, therefore, what we can say, what is IB? IB is basically IC by beta. So, just input those values, we just obtained what is the value of IC. IC is 5 milliamperes. What is the value of beta? Beta is 250. Therefore, we will get the value of IB as 20 microamperes. Now, using these values also we can understand, we know that IC is in the ranges of milliamperes and IB is in the ranges of microamperes. Fine. So, that is the end of the first question. Quite easy, we just need to understand how we should perform what is the complete methodology to obtain the result. Fine. Let us move to the next question. The next question is being asked that calculate the value of V1 when the transistor is switched on, and the second question is find the ranges of V1 for which the transistor is switched off and switched on. So, in the C, quite evident if the range is being asked. So, basically we just need to understand that we need to change the value of VBB. If for one case we need to use it as 0 volts and for another case we need to use it as 5 volts. Okay. So, first of all let us calculate the initial part. So, here for the switched on portion, determine V1, the input voltage at which the transistor will go into saturation. So, first is for saturation part here. So, for saturation what we will require, first we should know what is the input voltage being asked. that input voltage input is being used from this sense, correct. So, that input voltage is nothing but equal to VBB, because this will be only input voltage, correct. So, VBB is nothing but equal to simple Kirchhoff's rule application already done very many times, is nothing but equal to IB RB plus VBE. What is the value of IB? IB just was being obtained at saturation as 20 microamperes into RB, RB was given to you as 100 kilo ohms plus VBE. This VBE is also given to you when it is saturation, it is 0.8 volts. Okay. Therefore, the input voltage being obtained is 2.8 volts. Okay. The value of input voltage below which the transistor remains cut off is given by. So, you just need to remember this, that it is being said to be remaining cut off. VIL should be 0.6 volts and VIH should be equal to 2.8 volts. Okay. So, this is the first thing we obtained, that is the determine V1 when the transistor is switched on. Now, what will happen between 0 volts and 0.6 volt, the transistor will be in switched off state, quite evident. This was also been explained when we were understanding the concept of your transistor as a switch. So, between 0 to 0.6 volt it will act as in the cutoff region and hence it will be switched off state. Between 2.8 to 5 volts, because that is the maximum value which it can attain, it will be switched on state. So, note that the transistor is in active state when IB varies between 0 to 220 milliamperes. Fine. Therefore, in this range IC is equal to beta IB is valid. In the saturation range IC is less than equal to beta IB. So, these are nothing but facts, they are just explaining us so that we can use it in some other question. So, they are just saying that for the value of active region of basically the value when IC is equal to beta IB is valid in these ranges, and in the saturation range what happens is in saturation range IC can be less than also or equal to also beta IB. This is the first point, and next point was that determine V1 when the transistor is switched on is basically these regions here. Okay. So, they are just asking when it is switched off. So, it is switched off between 0 to 0.6 volts, and when it is switched on it is 2.8 to 5 volts. Okay. So, that is how the working of transistor as a switch can be understood. Okay. Fine. So, these all things I have made you understand. V1 will be nothing but 2.8 volts here, because that is the value at which the input voltage at which the transistor will be switched on, minimum value of voltage. Fine. Let us move on to the next concept. So, for a CE transistor amplifier, the audio signal voltage across the collector resistance, please ignore this, I think this diagram is of no use here, it is used here. Okay. So, just ignore this diagram, just look at the question. So, for a CE transistor amplifier, please remember it is a CE, that is common emitter, the concept which we understood just right now. Okay. So, the audio signal voltage across the collector resistance of 2 kilo ohms is 2 volts. Suppose the current amplification factor of the transistor is 100, what should be the value of RB in series with the VBB supply of 2 volts if the DC base current has to be 10 times the signal current? Everything is given to you, just need to calculate, just try to write each and every concept line by line and you can understand the problem. So, also calculate the DC drop across the collector resistance. Okay. So, let us understand clearly. So, first of all, what is the output AC voltage given to you? The output AC voltage given to you is 2 volts. Okay. Using this 2 output voltage and this value of resistance given to you, can we calculate the value of current? So, current is nothing but equal to 2 upon 2000, which will give you 1 milliampere. So, what is the AC collector current? Please remember, it is not the value of capital IC, it is just the value of AC collector current. Okay. The current which is being obtained or generated due to a AC signal. Okay. Fine. So, this thing is explained. Next thing is the signal current through the base is therefore given by, so simple as the value of beta is given to you, and we also understood in the previous discussion also that the value of beta for AC and DC are very same. So, even if it is not given here, we can understand that the value of beta AC is equal to beta DC is equal to 100 here. So, let us use this signal this value of beta for our calculation purpose. So, therefore, the signal current through the base is therefore given by IB, which is equal to IC by beta, which is nothing but equal to 1 milliamperes by 100. So, normal just simple calculation, IC was just obtained as 1 milliamperes and therefore, we will obtain the value of IB as 0.010 milliamperes. Okay. Next thing is, so we are just trying to, first we were at the output, now we have came into input Kirchhoff's input Kirchhoff loop or input loop. So, now the DC base current has to be how much? So, it is given here that if the DC base current has to be 10 times the signal current, that is what is the value of capital IB. Capital IB is nothing but equal to 10 times 0.010 milliamperes, that will give you the value of 0.1 milliamperes. Everything is written in the question, we just need to understand it mathematically. Okay. Now, simple mathematical Kirchhoff's rule application, just rearranging the terms. Finally, we will get RB is nothing but equal to change in the voltages VBB minus VBE upon IB. VBE is given to you as 0.6. We can assume also, why it is being assumed, because this is one of the factor which we all generally use in amplifications or in switches. If it is generally, if the question is being asked in exam, it will be given, but if it is not given, you can generally use it, you can remember this value of VBE as 0.6 volts. Generally in exams it will be given, but if it is not given, use it as 0.6 volts. So, I think everything else is given to you. VBB is given to you as 2 volts, right. VBE is given to you as 0.6, we just assumed it, and this IB we just obtained as 0.1 milliamperes. Just putting in the results, we will get the value of RB as 14 kilo ohms. Therefore, the DC collector current IC is nothing but equal to 100 times 0.1, which is 10 milliamperes. How is this thing obtained? Because this value of beta is given to you as 100. So, this is one of the peculiar or typical example. We need to understand that the value of beta here in this sequence, the value of beta AC was being used, correct. Beta AC was being used, and here beta DC was being used. Okay. So, that is one of the reason this question was being put up here. So, please understand that value, if nothing is given about amplification factor, we need to assume that the value of beta AC is equal to beta DC, first concept, and second concept is that if the value of VB is not given to you in the question, we need to assume it to be, we can assume it to be 0.6 volts. Fine. So, I think that is a question. Let us move on to the final concept of transistors, junction transistor, which is basically feedback amplifier and transistor oscillator. Okay. So, before understanding this complete concept of feedback amplifier and transistor oscillator, first of all let us understand what does it mean by feedback amplifier and what is the meaning of transistor oscillator. Okay. So, first let us look at this figure A here. Okay. So, what actually happens that the output voltage or the output of an amplifier generally is being a part of that is being generally again being sent as an input. This recurrence of sending of the output signal, part of the output signal into the transistor amplifier is basically called as a feedback network. Okay. I will just iterate it again. So, basically let us suppose there is an input, let us suppose there is an output, there is a black box which is being written as transistor amplifier, some input will be there, it amplifies the signal, therefore, we will get some amplified value. A part of that amplified signal is being put up into again into the input signal. We again obtained some value, again a part has been again input into this signal. Okay. So, this again and again or this recurring process of putting or taking a part of the output into the input signal again is basically a mechanism or network which is called as feedback network. Such type of amplifier which uses a feedback network is called as your feedback amplifier. Okay. So, I think the first concept is being understood. Why do we do it? I will try to explain to you when the time comes, but for now just you can understand what is the basic definition of feedback amplifier. That was the first thing. Second thing is transistor oscillator. Okay. So, transistor oscillator is basically a device in which the value of the amplitude of any input signal is always constant. In other words, we can say that the value of the input signal or sorry the output signal basically does not get damped, and undamped if we are passing the signal through an oscillator, then let us suppose if this is the input signal, if we try to process it through an oscillator, then this will be your output signal. So, this is the basic work of an oscillator. What does an oscillator do? Basically, oscillator is a device which is being used to convert an damped signal into an undamped signal. Fine. So, that was the basic two definitions of the heading which we are trying to understand now. Now, let us look at just the complete theory which is written here. If the concept arise, it is important, I will try to convey to you and then we can move forward. Fine. So, in an amplifier we have seen that a sinusoidal input is given which appears as an amplified signal in the output, quite evident. The basic definition of amplifier is being explained here. This means that an external input is necessary to sustain AC signal in the output for an amplifier, quite evident, because we will need some another input, so that it will pass through this amplifier and then we can obtain a output magnified or output amplified signal. So, what happens in an oscillator? In an oscillator we get AC output without any external input signal. So, that is the basic agenda or basic way in which oscillator works. So, we get this AC output without any external input signal. We just try to we just use the output as an input, output as an input, and we finally get a output for the oscillator wave or output of the oscillator signal. In other words, the output is an oscillator that is self sustained. So, it can sustain it it is self sustained, means nothing more obvious explanation is required here. Let us move forward. To attain this, an amplifier is taken. So, first of all let us take an amplifier. Okay. A portion of the output power is returned back. So, this returning back is basically called as feedback to the input in phase. Please remember, it is very important, it has to be input in phase, as in if we are trying to, this is the actual part which is going inside, and let us then the feedback part should also be in the same phase. This is correct, but if it is something like this is wrong. If it is even let us say something like this, then this is also wrong. It should be exactly in phase. So, this is the first point with the starting power. So, this term is basically called as positive feedback as shown in figure A. So, this is how a positive feedback works, in which we try to return a part of the power in phase with the input signal or in phase with the starting power. The feedback can be achieved by inductive coupling. The feedback can be achieved by inductive coupling. So, these induction etc. were being explained in some another chapter. So, mutual inductance and self inductance is being explained here. So, the feedback can be achieved by inductive coupling through mutual inductance. So, as you can see, there is a mutual inductance being happening here. I will try to explain it, or LC or RC networks. So, different types of oscillators essentially use different methods of coupling the output to the input apart from the resonant circuit for obtaining oscillations at a particular frequency. For understanding the oscillator action, we consider a circuit as shown in figure B. So, let us understand this figure B first of all, and then we will move forward, in which the feedback is accomplished by inductive coupling from the one coil winding to the another coil winding T2. So, let us suppose this is the first coil winding T1 and this is the second coil winding T2. Okay. So, I will just try to explain this diagram here and then we can pause this lecture here. So, see clearly what is trying to be explained here. You can see that this is the NPN transistor here. So, what actually happens, that let us suppose this is the first input signal, let us suppose. Okay. So, because of this difference, there is an inductance happening. Due to this inductance, we can see a charge being formed here. There is a charge being formed here, and this charge in the capacitor keeps on forming till the point this value is not attained as similar to the value in the positive direction. What happens in negative direction? What happens? So, this was for positive direction. What happens in negative direction? There is a reverse charge being obtained. So, this reverse charge is being obtained till the point in which this value is being decreased such that no more power or no more charge addition can be obtained. This is a very peculiar concept, peculiar type in which we can understand this. So, basically the basic crux is that the capacitor keeps on charging, and this due to increase in the charging of the capacitor, the amplitude keeps on increasing. This amplitude is basically that amplitude which is being undamped, which is being damped. Okay. Now, next thing is till what time it will get charged? It will only and only, the amplification will occur only and only till the point at which the capacitor is at its maximum charge. When its maximum charge is not happening, then it will not further increase. Quite evident that this is the this is the maximum charge value, it cannot obtain further from this portion in the positive sense. In the negative sense, what will happen? Let us suppose this is the negative charge, this is the positive charge. Again mutual inductance will happen, and to this mutual inductance it will keep on decreasing, and the negative sequence, this will change into this. Okay. I think a little scale issue is here. Okay. So, this will change into this. Okay. No change in frequency, no change in another sense, only and only amplitude will keep on changing from damped to undamped. Okay. So, that let me stop it here only. I will just try to explain the concept which are being remaining in the next part. So, everything I just explained here is being written in some sort of another. We will try to understand whatever is written here, and finally, the only thing which is required here we should understand is that the resonance frequency is nothing but equal to 1 upon 2 pi root L C. So, the value of L C may be given to you, and we need to calculate the value of resonance frequency. Fine. So, let me stop it here. So, the course progress for you, we have completed the introduction, classification of metals, conductors and semiconductors, intrinsic semiconductor, extrinsic semiconductor is also completed. In extrinsic semiconductor we understood P and N junctions, P type conductor and P type semiconductor and N type semiconductor. Then in P N junction we understood basically the accumulation of both of them. Then in semiconductor diode we understood reverse biasing, forward biasing, etc. Then application of junction diode as a rectifier, full wave rectifier, half wave rectifier and so on. Then in special purpose PN junction diodes we understood Zener diode, photodiode, solar cell, solar diode, solar cells, etc. Then currently we are on the 9th, that is junction transistor. This is almost complete, only 2-3 slides are left, and then we will move on to the final discussion regarding digital electronics and logic gates, and a small discussion regarding integrated circuit is being left, and that will be the end of this lecture series on semiconductor electronics. So, that thing being said, thank you so much.